All right, welcome to your heat transfer, intro to heat transfer pre-lecture. So we've talked about enthalpy and we've been talking about three ways to calculate enthalpy. And now we're looking at more specifically, how do we calculate the heat exchange between system and surroundings or between two objects? So let's just remind ourselves of a couple things about one, what we already know to be true through our everyday experience, okay? We know that heat exchange occurs between objects of different temperatures, right? Temperatures, and remember, temperature is really a measure of energy, so different temperatures are energy. So we know that heat, or at least we should know, that heat flows from hot to cool. It is never the opposite way around. So we always say that heat flows from high kinetic energy spaces or objects, okay? High kinetic energy to low kinetic energy. So when we say, oh, my ice cooled down my water, that's a very like layman street term. It's not true at all. What you really should be saying is, oh, my water lost heat to the ice. Yeah, and my ice absorbed it. Okay. But we also know, hopefully from elementary school, or maybe not elementary, sorry, junior high, or maybe even a little bit of thermodynamics and physics, that the actual definition for heat is actually defined as, okay, the energy transfer from one body to another due to the change or the difference in temperature. So notice that the concept of heat is actually dependent on the inherent ability for it to be exchanged. Okay, so heat exchange doesn't continue on forever between objects at different temperatures. We know from real world experience that it eventually stops. And we call this stopping point indicative of when thermal equilibrium has been reached. Okay, and this is thermal equilibrium is the point at which two objects stop exchanging heat as they have the same temperature, or more particularly average kinetic energy. Okay. And so when we look at heat exchange, we are always looking at or examining the exchange between a system, and you could call that object one, and surroundings. You could also call that object two, depending on the context of your experiment. This also could be labeled as object two. Okay. But we're always looking at two things, and we often label in terms of system versus surroundings. So when you've heard the term open system versus closed system, and in a lab experiment, is this an open system or a closed system? Okay, when you hear that term, what it particularly means is that, am I a system where mass and heat is exchanged between system and surroundings? Or am I a closed system where only heat is exchanged? Okay. And particularly for us in this unit, we really want to know, are we an insulated closed system? Okay. Where neither heat nor mass is exchanged between system and surroundings. So that's just a little terminology for you to understand the boundaries in which we often have to define when discussing heat transfer and making calculations. All right. As well as it's just a generic term that you should understand when creating the parameters for an experiment. Okay, so let's look at a really tangible way of understanding how we can track and quantify and qualify or like describe heat transfer. And phase changes between states of matter are like one of the best example. So phase changes are physical changes, right? A physical change slash process. Okay. And that are dependent on heat exchange and IMFs, intermolecular forces between the particles. So just a quick reminder, an endothermic process doesn't have to be a chemical reaction. It can also just be a physical process that requires intake of energy. So going from a solid to a liquid to a gas is an endothermic physical process. Okay, exothermic physical process is going from a gas to a liquid to a solid. I actually release energy as I cool. More energy from my system, whatever object's cooling, is going out into the surroundings, allowing my system to get colder and take on a more solid form. So we actually have, of course, quantitative values for each process. And depending on the substance, right, we know to be true from real world experience that each substance holds unique heat energy requirements to make these physical transformations. So we call that the heat of fusion is the amount of energy required, okay, to be absorbed, so transferred into the system, to be absorbed, to melt. Oops. To melt a specific substance, all right, at melting point, at the melting point temperature. So it's how much heat is actually having to be absorbed to begin the melting process, to get a substance to begin melting at its temperature, okay? Remember, temperature is not heat, okay? And maybe I should make that really clear actually while I'm thinking about that. As I continue talking about temperature, okay, and heat, while they are heavily connected, they are not the same. Remember, heat is dependent on, defined as the energy transfer due to temperature being different. Temperature is a measurement. Heat is kind of an inherent energy. Okay, temperature is a measure of energy. Heat is the actual kind of subject that we're talking about. All right. And so one thing you should know is that the heat of fusion for water is equal to 334 joules per gram at 0 degrees Celsius. So we know that like water melts at 0 degrees Celsius. Well, how much heat energy is the water molecules having to absorb at that 0 degrees Celsius measurement point? 334 joules for every 1 gram of water is required to begin melting water from solid to liquid. Okay. And of course, we should be aware that if we were to flip this, the opposite of heat of fusion is known as heat of freezing, which is kind of like, or heat of condensation, which is like kind of opposite of what you would think, like there isn't heat involved. It's just the opposite term. So heat of freezing or condensation would be the reverse of this. Okay. Slash condensation. No, whoa. Why am I saying condensation? Just heat of freezing. Good God. Whew. Okay. And it would be the flip value. So for like water, heat of fusion for water would be, goodness guys, heat of freezing for water would be the opposite of heat of fusion. So it'd be negative. I'd have to lose 334 joules per gram at 0 degrees Celsius to go from liquid to solid. Okay. So as you can predict, that heat of fusion concept takes care or helps explain the transformation between a solid to a liquid. But what about the transformation between liquid and gas? Well, we have another term known as heat of vaporization, right? To create a vapor. So this is, of course, I'm just going to copy and paste this, the amount of energy, okay, required to be absorbed to melt, and not melt, but to vaporize to vaporize a specific substance at boiling point. Just going to modify this at boiling point, okay? And so for water, the heat of vaporization is equal to 2,250 joules per gram of water at a temperature of 100 degrees Celsius, okay? So that means I need 2,250 joules of heat energy for 1 gram of water moving at 100 degrees Celsius or 100 kinetic energy rates, 100 kinetic energy units, to begin the process of having my water particles go from the liquid to the gas phase. All right. And of course, we have a similar thing here, if I cannot mess up the wording again, where we have the opposite of heat of vaporization is heat of condensation. Okay, heat of condensation. So condensation, and that would be the opposite of the value given for heat of vaporization should be negative. I'd have to lose 2,250 joules per gram of heat energy, all right, for me to be going from liquid or gas to liquid, okay? So keep in mind that all of this heat energy is being applied in a way, right? Particularly being applied to break the IMF. So this heat energy that you're losing or gaining with heat energy, okay, is used to break apart or weaken the IMFs. And I guess I should be more specific, is heat energy absorbed, right, is used to break apart or weaken the IMFs, right? So for example, between water, we have a ton of hydrogen bonding, which is the strongest type of IMFs. So what we would say is that our hydrogen bonds are dipole-dipole IMFs that are also present, because if I have the strongest type of IMF, I also have the weakest, everything below it. And our LDFs, which all molecules have, all of these IMFs are weakened, okay? Are weakened with increasing heat absorption. Oops, sorry. Increasing heat absorption and kinetic energy movement, right, of the particles represented by higher temperatures. All right. But of course, we are keeping in mind that no actual intramolecular force or bond is broken, right? So please make sure you keep that in mind. So we have a cool diagram known as a phase change diagram, aka heating curve, that we can use to demonstrate the concept of heat absorption and IMF and phase change, okay? And so what we have here is in this heating curve, we have added heat in joules on the bottom and a temperature on the y-axis. And what you'll notice is we have some unique regions here. We have inclining regions, and then we have plateaued regions. All right. And so what you should notice is that one, okay, phase changes don't occur until enough heat is obtained. Okay, don't occur until enough heat is absorbed. Okay, represented by the incline, and right, we have to reach our boiling or melting points, or melting point temperatures. Okay, so what region would that be? That would be all those blue regions. It's the inclined regions, those blue regions. Okay, also notice that once ample heat is obtained, is obtained, okay, we see a plateau, okay, in temperature, aka kinetic energy of the particles, in temperature as the particles use the heat energy to break IMFs or weaken IMFs. So here you see that distinctive nature where temperature and heat are truly different, okay, concepts. So what we see then is that pink region is where we see our heat of fusion plateaus, where we see the amount of heat necessary at a given temperature, at a given kinetic energy particle movement required to actually thoroughly break apart the IMFs to create the transformation in phase, right? So we see a plateau, it's your plateau regions. All right. So that's kind of all you need to know about those things. Really, we just want you in the AP to be able to read and explain the concepts. And then we will teach you some of the basic math in the next lecture series. But let me just kind of summarize in general what's happening. So one, if you were to reverse direction of phase change, right, you'll read the graph from top right down to bottom left, you would be reading heat of condensation, heat of solidification, or freezing. Transformations. And so just as a summary, the negative heat of condensation is the negative of heat of vaporization. And going from a gas to a liquid. And heat of solidification is going from a liquid to a solid, and it's going to be the negative heat of solidification or freezing, right? You could call it freezing. Oops, freezing. Is going to be the opposite of heat of fusion. And oftentimes in books, you might hear it called latent heat of fusion, latent heat of vaporization, latent heat of condensation, latent heat of solidification. This is just a terminology. Recognizing the plateau or heat absorption, or I guess you could say heat flow, because it could be absorption or release, heat flow at a constant temperature. So that latent heat term is just trying to recognize those plateau points where it's not just heat of fusion and it's like it's heat of fusion over a constant temp. It's heat absorption over a constant temp, heat release over a constant temp. So sometimes you might hear terminology wise it be called latent heat. Okay, it's just an additional specific way that we say it to convey the nuanced meaning of what we're trying to describe. Okay, so let me write just for example, you might see it written as latent heat of fusion, right? Might be one way that you see it in another textbook, or that the AP might put it in a prompt. It's not a different thing. It's just a different way of saying it. So here's a quick recommendation. I would highly recommend that you guys memorize the following values if you haven't already, that the melting point for water is 0 degrees Celsius. The boiling point is 100 degrees Celsius. You might also want to be familiar with it in Kelvin, right? Okay. And as far as a takeaway, please, for the AP, be able to read or interpret and explain phase change diagrams. And of course, phase change in general. All right, guys, really good job. And I'll see you tomorrow or whenever the next class period is.